Okay. Okay, let's get started. How many students? 5, 10, 20, right? So 49 students, they register for this class. Now 20 only. Okay. Okay. That happens. That happens at the end of semester. Okay, let's continue. Talk about our demo. Let me show you the before and after status. So that is a before status, right? So before enabling MMU, before creating page table, that is called flat mapping. Flat, right? Flat mapping is virtual space, right? Virtual space and physical space. Physical space. Virtual space, physical space. Flat mapping, no translation, right? The same address. Physical address is equal to virtual address. Right? These two are equal. Flat mapping, flat mapping. Physical address is equal to virtual address. No translation, just no equal, just connected, right? So you have been doing experimentation with flat mapping so far. Okay. So now we are doing address translation with page table. So before enabling, so in the demo code, before enabling memory management unit and creating page table, we do this. We are storing this data 11223344 at those locations. So 150, that is first location of second 1 megabyte, 0x11. So location is 150. So that means 5 zeros, right? 20 bits. You do the math, right? 2 to the power of 20. So that is the first 1 megabyte, second 1 megabyte, third 1 megabyte, and so on. Right? You can do this, right? So we are storing 112, first 1 megabyte location, and 22, second, third, sorry, 1, 2, 3, third, 1 megabyte location, and 3, 3, 4, 4. So that is done before creating page table and enabling MMU. Right? So to enable, to create page table and enable MMU, you have to touch. Three system registers. So first one is TTBR0, translation table base register. We create this translation table, right? So inside the CPU, inside the processor, we have TTBR0, translation table base register. That's supposed to be a program to point the start location of page table. And second, system register, TTB translation table. What does that stand for? BCR. Translation table, what? B. So many system registers, right? So this one. Base control register, translation table base control register. So using this control register, you can do this. The important thing is PD0 and PD1. Actually, PD0. Take a look at only PD0. PD0 means what? If you set this pin to 1, you are disabling, right? A translation, this one, D, disable. Translation table work, disable. So that means if you set, that's it. If you set TTBCR PD0, disable, right? Disable to 1. Then you are disabling hardware-based page table work. Hardware-based, right? If you have TLB bits, then what should happen? You have to do page table work, right? You have to find out the specific entity, PTE, and load that entry to TLB, right? That should be happening. So that process should be done by hardware or software. Okay? So disable means you are disabling that hardware-based page table work, right? Then what happens is exception will be generated. Translation fault. TLB means will generate exception. Prefetch exception, prefetch abort, or data abort. If you remember, right, interrupt discussion, we have a data table. There is an entry or prefetch abort and data abort. If TLB miss happens during instruction patch, prefetch abort, TLB miss happens here, then there is prefetch abort. Prefetch abort exception if TLB miss happens while you are accessing data, instruction patch and data, right? TLB miss, then data abort. Data abort, right? So exception, right? So we don't. So we want to do what? So we want to set this bit to 0. We want to enable hardware-based page table work. So let hardware do the page work and find out the entry and load it into the TLB. Let hardware do that job. Right? So we don't want to do that by software. Right? So we want to set translation table-based control register to 0. That is 1. And then and the last thing you want to do is SCTLR, system control register. System control register. Using this system control register, if you remember cache discussion, we enabled or disabled the cache with that register. So MMU is enabled or disabled with the same register. There is a LSB, least significant bit. System control register, last one. LSB is MMU enable or disable. So you have to enable MMU. Okay? TLB is located inside. Hardware module called memory management unit. That guy is doing TLB lookup. TLB lookup, right? You are supplying virtual address. Somehow you have to look up TLB. Right? So there should be some hardware. Hardware should pinpoint. Okay, I need to I select some TLB entry and do comparison. Check out if it is TLB miss or hit. That whole process should be done by MMU. Okay, 3 system registers should be set to enable. Then we want to create that mapping. In the demo code, we want to create that mapping. We want to change just for fun. Right? First, 1 megabyte flat mapping, okay? No translation. But second, virtual section 1 is mapped to third physical section, PS number 2. And this one, and so on. We want to create an mapping, some anomaly, right? Just for fun. Okay. So then I want to. So after this mapping, we want to access. Using LDR instruction, memory read instruction. R6. Then R1. R1 contains one 100,000, right? So that location. Then according to the translation table, 1,000, 100,000 is that to that. So physical address 200,000 will be generated. So even though you are accessing in your program, you are accessing that location, but in reality, you are accessing this data, not this data. Right? So that's the demo program. So let me show you. So this demo. So let's follow the program together. So we are. So this is an enable, right? TTBR, translation base register setup, right? That TTBR setup code, and TTBCR, translation table base control register. Okay? Or hardware-based page table work. For hardware PD to 0. That means hardware-based page table work. Then you are enabling MMU. Okay? So before that, this code, this simple code is storing 112244, 112244 at those locations. So with the flag mapping, you are storing this data. Then enable page table. Okay. Then flag mapping, enable page table. Then after that, you are accessing R0 is what? R0, 100,000. R1, 200,000. Okay. R2, 300, and so on. Okay. So let me run this code. Register, so and memory dump 100,000, okay, and 200,000, 400,000, right? Memory dump. So some data is already loaded because I executed this program before I come to the class. Okay? So let me anyway run it. Bye. So vector table, we want to use our own vector table. Right? This one. Then read out some system registers. This register, that register, PCR, TBR, just a read, right? I'm just curious what information is stored in that control register. Just read. Right. Just read. So disable MMU first, because we are going to use a new page table. Disable MMU. Then with this instruction, you can invalidate everything. Invalidate, right? Just in case, right? So TLB has some, just in case TLB has some translation information. Invalidate. Okay, remove everything. Remove everything from TLB. Remove everything from the cache. Just in case. Then, okay, so with the flag mapping, we are storing data. Okay, so we have already data. Okay, here, but let me do it again. So read out just in case. Okay, R10, R11, R12. To make sure the data is actually placed in the memory. So we have to make that sure. Okay, R10, R11, R12, right? So data correctly retrieved, right? R10, 11, 12. Then enable MMU. Enable MMU page table setting, right? Page table. So where is that located? Page table. Curious, right? Page table recreated is this one. CSD MMU table. we are curious where the table is located, right? So you can check out what? Symbol table, right? Symbol table compiler created, right? CST. Symbol table compiler created, right? So that is located from 8,000. So location of this table, 8,000. So we impose some restriction in the linker script, right? Because that table should be what? Should be the start location should be aligned at 16. It should be located at 16 kilobyte aligned location. 16 kilobyte aligned location. Because it's a table size. 4,096 entries. Each entry 4 byte multiplied by 4. That means 16 kilobyte. Page table size. So that should be located at that location. So this number is 16 kilobytes aligned location. So this is what? 2 to the power of 14. That means all 14, 14 bits. Last 14 bits in the address. Last 14 bits supposed to be all 0. That is 16 kilobyte aligned location. So upper bits, anything is okay. But last 14 bit should be 0. That is, so then this one, right? So we have 12 zeros, right? 12 zeros, next number, 8 is what? 1, 3 zeros. So 12, 13, 14, 15. So one more 0, then 1. So that is 16 kilobyte aligned location, 1 of 16 kilobyte. So again, this linker script, if you check out this linker script, then we impose that restriction, right? That MMU table, page table should be aligned at that 16 kilobyte location, right? The CST MMU table. So the symbol is here. CST MMU table. Let's go back to the debug. Okay, we are here. Then, so this one you are setting TTBR register, and then TTBCR, hardware-based page table walk, enable. Then finally, MMU enable. So we are disabling, just in case, right? We are disabling instruction cache and data cache, only enable MMU. Only MMU. Okay. Then see, you see something, right? One location 1, you are displaying 1, 2, 2, 1, 4, 4. Now location 2, right? 200,000 supposed to have 2, 2, but look at this memory dump. Look at the memory dump. Okay. Now 4, 4. The memory dump got changed after reflecting, after updating, after using that, new page table. Then 4, right? Location 4. Supposed to have 4, 4, but now it has 1, 1. So page table. After reflecting page table, this memory dump, this debugger displays a new memory, dump. So it is a memory dump. Displaying what CPU sees. CPU sees that memory dump. Okay, so let me run this code. So now, R0, you are reading from what? You are reading from first 1 megabyte. Supposed to have what? So according to, we don't have mapping. So according to that mapping, right, 1 is mapped to what? Pitch call section number 2. So it will read to 2. Right? So F5, check out R6 register to 2. Yeah. Okay. So second memory read instruction, you are reading from 200,000. Okay, that is mapped to what? That is mapped to pitch call section number 4. Pitch call section number 4. So R1 will have 4. Okay. So R2, you are reading from this location. Okay. So then there is mapped to PS number 2, pitch call section number 2. So you get 2, I think. Right, 2. So finally, 400,000 reading from that 1, 2, 3, 4, 5 this location. Then you are getting what? This one is mapped to PS pitch call section number 1. So you are getting 1, I think. Okay. But one thing is, if you run this code the first time, I think we have some issue. Debugger is not displaying. This debugger is not showing the correct the memory dump for some reason. I don't know. But if you run it a second time, it works fine. So okay, we have some issue with the debugger. So if you have some problem, then run it again. Okay. And if you fix this problem, let me know. I can give you some extra point. Okay. Okay. Any question about this? Some toy example, right? So virtual memory, physical memory, the translation, the toy example. But the important thing is our computer, our Windows, Linux are running based on that virtual memory. So your application, when Intel CPU or ARM CPU in your smartphone has ARM CPU, right? Run application that is fully utilizing this virtual space. Each application is fully monopolizing this virtual space. And operating system is creating page table for each application. You do context switch. Then operating system is creating new page table. This one is for task number 1, your hello world program. Right? You do context switch. Right? Then run task number 2. Right? And then pull in new page table. So TTBR is supposed to be pointing new location. Every time you do context switch, the CPU load new page table. Right? Then TTBR will be updated. So that is important. Okay. Then let's move to so we have been talking about the most simple translation mechanism in Cortex A9. So let's go back to here. We've been talking about this section, right? Section translation is most simple thing. But Cortex A9 is providing 4 different page sizes. Okay, so 1 megabyte, 16 megabyte, and small page and large page. Okay. Super section and section, you need only one page table. Okay, one page table, but small page and large page, you need 2 page tables, 2-level page table, 2-level. And before we talk about small page translation, and why do you think computer architect created two page tables for address translation. One page table is simple, right? And easy to understand. Why you need multiple page tables for address translation? Any idea? Yes, good point. Right? Yes. That is, one serious problem. Think about Intel processor, 64-bit Intel. So page table itself is taking huge amount of memory. If you don't have multiple level page table, Intel 64-bit architecture. x86 64. Then program counter or instruction pointer. Instruction pointer or program counter. That is actually 64-bit. I told you, but 64-bit is too big. So that is creating too big space. So Intel decided to use 48-bit instruction pointer. So that is coming out. That is virtual. Then here B is current address. Then how big space you are creating? Virtual space. Virtual space. 2 to the power of 48. 256 terabyte virtual space. Then assume that page size is 4K byte. You divide this virtual space with 4K byte. Each one is 4K byte. 4K byte pages. Then how many pages are there? Divide this number by 4K. 4K byte. Then tera, right? And K. Therefore, 64 gig different pages you have, right? Then how big the page table would be, right? So this one, virtual page number 0, virtual page number 1, the last one, virtual page number 64 gig minus 1. Right? So then you need a page table entry. Okay, we have a page table. Then you need one entry for each virtual page, right? That means you have 64 gig page table entries, PTs. Assume that each one is 4 byte, right? Each one is 4 byte. And how big the page table would be? Multiply this number by 4. 256 gigabyte page table. How big your main memory in your computer? Your computer has probably 16 gigabyte main memory, right? 8 gigabyte main memory. Your main memory cannot hold even page table. Big problem, right? So one big page table is not solution. The solution, right? So the solution. So in fact, let me show you. Page table. Page table. How many page tables are there in Intel? Right? x86. Get this. Okay, this is the one. Right? So Intel is using how many page tables? First level page table, second, third, and fourth. 4 page tables for address translation. Right? So 48 bit, right? 0 to 48 bit address. (4720) virtual address. So that is divided into 9 bit. This one is 9 bit. 49, 48. Another 9. 9. And 12. Page offset. Page offset. 4K by page offset. So so that is offset. So within 4K by page. So using this 9 bit, you need the first level page table, and that is indexed with this 9 bit. First 9 bit. And that means you have 5, 12, P, T, E page table. In the first location, I told you, right? Control register 3. CR3 right there. CR3. That is pointing the start location. Page table. Okay. So what does that mean? What does that mean? Then it means but it means what? It means 39 bit, right? 39 bit. That means 39. 512 gigabyte. 39 from here to here. So each entry is providing translation information for each 512 gigabyte virtual space. This virtual space is divided. I'm trying to explain the meaning of this table, first table. So that virtual space is first divided into 512 different chunks. 512 different chunks. Right? Each one is 512. Each one is 5 same numbers. So that's gigabyte. Each one 512 gigabyte. Then 256 terabyte virtual space. So multiply these two. 256. So the first entry is trying to provide translation information for first 512 gigabyte. And second entry is trying to provide translation information for second 512 gigabyte. The rationale is, why do you want to do this? Because when you run your application program, you are not using this full 256 terabyte. Only small fraction of virtual space would be used in your by your program. Then why do you want to have full translation table for full this virtual space? I remove this, right? So the thing is, if you need only translation information, if your program is using this only small, not small, but the first 512 gigabyte, and never use that virtual space, then this entry says, okay, I'm going to first entry says, okay, look at check out subsequent page tables. But for other entries, okay, you don't have to look at subsequent page tables. So no, you don't have to. Because we are only using this one. Okay. And next entry, next table. This entry is pointing the start location. Let's say this one, level 1 table, and level 2 table. level 2 table is indexed with that second 9 bit. And this PT is pointing the start location of L2 page table. It has also 9 bit, 2 to the power of 9. So 512 PTs. And if you do the math, what is that? 29. So each entry is trying to provide translation information 29 to 0 or 1 gigabyte. So let me make it this one is like the virtual space. Virtual space that is divided into 1 gigabyte chunks. So that means you have 12 different 1 gigabyte. Right? So this 9 bit. So this first entry is trying to provide translation information to the first this 1 gigabyte. Okay. Second one is trying to provide translation information for second. So think about your program. Probably your program is not using this 512 gigabyte space, only using the last 1 gigabyte or less. So second table says, okay, so only first entry, you need to look at first entry. Okay, so we are not going to use these examples. You see the solution, right? So the same thing goes to next table. Right? So that is the rationale. Okay. The why they are providing multiple translation table for address translation. Okay. Multiple page tables for address translation. Probably your 32-bit computer system, that wouldn't be a big problem, right? Because it's virtual space, right? Virtual space 4 gigabyte. Then think about small page, 4 kilobyte page. Then that is divided into 4 kilobyte pages. Then how many entries? 1 meg, right? 1 meg. You need 1 million PTEs. Multiply that by PTE size 4. You need only 4 megabytes for page table. So this page table size wouldn't be that serious problem, but 64-bit processor, you see the problem, right? Big problem, right? So you don't want to have one single page table because page table size is too big, super big. Okay, so let's move on to now small page, right? Small page, large page, you have to go through 2 different page tables. So if you understand this, then the other things are super easy. The other 2 page sizes. So let me explain with check out this. Translation example. So let me do. Generating 32-bit virtual address. 32-bit physical address. Main. So virtual address. So let me go here. Virtual address. 32-bit virtual address. The first page table. First table structure L1 page table. The structure of the L1 page table is the same. We are using the same page table. Same page table as this one. Okay, L1. Same PTE. same page table. That means this virtual space is divided into here 1 megabyte section. 1 megabyte section. So you have 4096 PTs. Each entry is providing translation information for this virtual section. Virtual section. 1 and so on. And in case of small page, 4KB page, the difference is the PTE. Let's say we are talking about this one. The page within virtual section number 1. So inside this virtual section, inside each virtual section, it was 1 megabyte, right? And we are talking about 4KB small page. And then inside this virtual section, how many small pages are there? Inside each virtual section, how many small pages? 1 megabyte divided by 4 kilobytes, right? That means you have 256 small pages. Right? Each virtual section, inside each virtual section, you have 256 small pages. So that means each the L1 page table. L1 page table is trying to provide translation information for this, for small pages within this virtual section. Second, so that is pointing. Okay, you need to look at second table L2 table. It has 256 pages. 256. So inside VS number there, you have same 256 small pages. And second entry is also same. Second entry, you need level 2, L2. And inside here, you have 256 pages. Each one is providing, providing a translation for 4KB. And same thing, right? This one is, okay, you need to look at L2. Level 2, page 10. And it has 256 PTs. Page differences. Simply because, inside each virtual section, you have 256 small pages. 256 small pages. So L1 table is based on section 1 megabyte. But you need translation for small page. So you need to look at second page table. Okay. So far so good. Any question? One. And page table is always page table. This one L1 page table, L2 page table. Page table is always indexed with virtual address. So using virtual address, if you remember that discussion, right? So we have 12 bit, sorry, 1 to 20 section, 1 megabyte section, and then we are talking about 4KB, 0 to 11. So that is 12 bit. Then 8 bit. 12 to 19 to 12. So using this virtual address, using this virtual 12-bit, you index, you search L1, you select page table entry in level 1 table. And again, if in the first location, start location, PTV, pointing start location. So you need to know. So page table is always searched. Not only L1 but L2. Page table is always searched with virtual address. Okay, virtual address. Then let's say you selected that this one, this entry. Let's say this virtual address you have 1 here. Everything is 1, 0, and but the 1. That means you are selecting this entry. Then that says okay, you need to look at second page table. That guy is pointing start location of second table. Then which PTE you need to select? You have 8-bit, right? You have this 8-bit. Select PTE in second table. You need the base location. That guy has information, start location information. Then how far? That is specified offset, right? So again, within this virtual section, let's say the first one is pitch per page number 0. Let's name it like this. Inside this virtual section number 1. Let me read it. Inside this virtual section number 1, the first page, let's say pitch per page number 0. Second virtual page number 0. Virtual page number 1. The last one, virtual page number 2. So inside this one neck virtual section have 56 small pages. Okay. So this one, L1 table. This one is this one first entry has translation information for virtual page number 0. Virtual page number 0. Okay. Second entry, translation information for virtual page number 1. And virtual page number 255. So inside this virtual section. So that is why you need to use this virtual address. Virtual address to index. So page table again. Page table is always searching. Page table always searching with virtual address. Then how do you get final pitch code address? Simple. That guy, right? Let's say this information. That guy has pitch card. It has pitch card page number. Memory inside memory. Right? So you have some so that is divided into 4K by pitch card page. 4K by pitch card page. So let's say which one? This one. So something is that is mapped to here. Let's say this one is per page number 2 million. Then it has 2 million. 2 million. This per page number 17. 17. 17. Per page number 17. So that means so how do you create this card address? this guy is talking about physical page number. So we have 32-bit physical address. So let me go 32-bit physical address. And last 12, no change, right? You are copying that information. That information to here. No change. This one is offset, right? That goes to here. Then you need this page. This one is physical page. Physical page number. So that entry, that guy contains no physical page number. This guy has physical page number. Does it make sense? Any questions? So take a look at this. Here, virtual section number 0. You have green is virtual section number 0, white virtual section number 1, and purple virtual section number 2. So this figure is showing mapping information of that orange page, right? Orange, okay, by page. The page is within virtual section number 0. That page is within virtual section number 2. That is mapped to here. This one is mapped to here. So for translation you need first level page table always, right? First level page table. TTBR contains start location. And then first entry is yellow, has translation information or first virtual section. That entry is pointing the start location of second page. And third entry here, that is pointing the start location, contains the start location of second page table. Okay, that's the one. And let's go through this PowerPoint. L1 descriptor also first, right? Level 1 descriptor. So level 1 descriptor, if you need the second page table, PTE should be that PTE, L1, PTE, level 1, level 2. Level 1 PTE should be populated with that information. Page table, right? Second level page table, that information. If you need second table, the entry should be populated with that information. That information you have 01. 01 then means look at level 2 table. Okay. So here, the address, physical address of level 2 start location. Level 2 table, right? Level 2 table, you need 256 entries, and each one 4 bytes. So page table size multiplied by 4, right? That means 1 kilobyte page table size. Right? That means start location. Look at that. By looking at that, right? You get some you get some feeling, right? Start location should be located at 1 kilobyte aligned location. because you can only specify 31 to 10. 31 to 10. The last 10 bit always 0. Less than from power of 10. Address. Last 10 bit is always 0. So then whatever you have in upper 12 bit, so that is 1 kilobyte or less location. So level 1 page table size 16 kilobyte. 16 kilobyte page table. Level 2, 1 kilobyte page table. So 1 kilobyte page table. Start location, you have some there's some restriction. They should start at 60 kilobyte or light location. 1 kilobyte per light location. So the last assignment I posted, let's check out. So let's talk about this last assignment. Okay. So before and after state, right? Before you populate main memory, before address translation with flat mapping, you populate main memory with those data. Okay, so 4 kilobyte, 4 small pages, right? Small pages. That page start from the location. Okay, the location and the location. Then I ask you to create page table. Okay, create page table. For the mapping, this mapping. So virtual address and the physical address. That's the first one, and the second mapping. Then add all the elements. Okay, using virtual address. Using this virtual address. Add all the elements within 12 kilobyte. 444. 12 kilobyte. Right? This all the data. Add everything. With this mapping, 2 different mapping. Then check out the result. Simple, assignment. So then the question is, you need to create a second 2-level page table, right? L1 page table, you know how to create page table, right? L2. So what do you have to do? L2. Check out this example. This one is a level 1 page table. Level 1. This example you have. Check out this orange code. You have 3 PTEs, page table entries. That word, right? Right? You have only 3 page table entries. Here, you have L1 page table. You have only 3. That example code, right? That is describing 3 PTEs. Then a second PTE. The first PTE, second PTE, third, last one. Second PTE says, okay, you need to look at this label. So in that example, second PTE is pointing some label, and that inside second page table, you have only 2 branches. Second level page table. But the one thing you have to be careful is alignment. Page table alignment, right? First table should start at 16 kilobyte boundary. Okay, and this one, second table should also start from 1 kilobyte boundary. So you have to change linker script. So to make sure that start from 1 kilobyte aligned location, second page table. Right? Are you guys with me? I'm confused. No response. Very confused. Are you guys with me or any question? It is very simple assignment. So what you have to do is create two level page table, adding the data. Adding the data is very simple, right? Adding the data. So the question is how to create two level page table. Okay, anything you want to ask before we move on? Time, 15 minutes. Okay, I want to finish the MMU discussion, theory discussion today. So let's move on to. So I'd like you to take a look at super section. It is a super section and large section, large page translation. It is very simple, actually. For super section translation, that is talking about 16 megabyte, right? So we are still using same L1 table, same L1 table, then 16 PTEs. 16 PTEs have same information. That is pointing to 16 megabyte, pitch called super section. That is the only difference. Let me quickly explain super section translation. The same thing is applied to large page translation. CPU and virtual address sorted. Sorry. 4 gigabyte virtual space. Virtual section number 0. Section 1 megabyte. 1 megabyte section. We are talking about 16 megabyte. Let's say there are 16 megabyte. We have 16 virtual section. Let's say virtual section number 16. This one, virtual section number 31. So 16 virtual section. That is 16 megabytes. And that should be mapped to. That should be mapped to this 16 megabyte physical super section. So the mapping, we need just one table. So L1 page table. 16 PTs, 16 PTs, 16, and then next 16 PTs for this. For this, and you have 16 16 PTs, right? Each one is pointing the same location. Each one is pointing the same location. same location, same location. So let me draw virtual address and physical address. Virtual address, and finally you want to get physical address. Physical address. Because we are talking about 16 megabyte super section. Then offset from offset is 24 bit, and this one upper 8 bit is talking about a super section number. Super section number, virtual super section number. Okay. So final physical address you will get is this one is offset. Right? Offset no change. Right? Offset this information simply copied to offset, and you need that information. You need. This one is physical super section. Physical super section. Then page table contains the physical super section number. Physical super section number. Same information. All 16 PTs have same information. Okay. So confusing thing is, then how do you index this L1 page table? L1 page table is still indexed using this fact. So that is using this one you are indexing L1 table. So L1 table is created based on 1 megabyte section. Each entry is talking about 1 megabyte section translation information. We are using same, right? Regardless of page sizes, we are using same L1 table. So L1 table always, right? We don't care, right? Super section, 16 megabyte super section, 1 megabyte section, 64 kilobyte large, small page, we don't care. L1 page table is always indexed with 12 because that is you have 4,096 entries. It is based on section. So we are still using this upper 12 bit to select the PTE. But in case of super section, those 16 PTEs have same information, right? That information same. That is pointing this one, same information. So indexing, you are using upper 12 bit, but offset, that is a little confusing point. There's some overlap, right? Some overlap here. So indexing 12 bit, offset, so you have some overlap, 4 bit overlap. So that is offset, right? Think about that. Right? It is, very simple. The first time, really confusing, right? But very simple actually. Any question about this? Okay, let's move on. So now last one is TLB, translation look aside buffer inside Cortex A9. So that is a TLB structure. Right? So you have two level structure. First level is called micro TLB. Second level TLB, unified TLB. Micro TLB, you have two separate translation look aside buffer. This one, the first one, is for instruction access. Virtual address, instruction translation. Sorry. Virtual address translation for instruction access. For instruction fetch. You look up this TLB. Okay. And for memory access, you look up this data TLB. Instruction TLB and data TLB. There are 32 entries, and the structure is fully associated. L1 is fully associated TLB. That means you have only one set. Think about the cache structure, same structure, one set, one zip. So everything is compared. All 32 entries will be compared. How do you compare everything, all 30 entries against this virtual address to check fitness, TLB fitness. But unified TLB, you have a second level TLB, 64 sets, and two-way set associated. You select one set, particular set, and there are two entries to compare. You select something, and your these two will be compared against this virtual address. So you miss L1, then L2 is there. L2 maybe provide translation information. If you miss L2, no choice, right? You have to go to the main memory to find out the PT. So page table is located in main memory at the beginning, and that is row 2, level 1, and level 2. If you miss. Okay, that is one. And this one, who asked the question? Who? You name? Who asked the question? You asked the question, right? So inside TLB, you have this very important information: address space ID. Space. So I told you, right? Each application is using this full virtual space for execution. Task 1 is using this full virtual space. Task 2, context switch. Task 2 is executed. Then T2 is using this full virtual space. The question is, TLB contains translation information, right? If you have only pitch call page number, some attribute. Okay. Then the question is, how do you know that translation information is for task 1, or task 2, or task 3? How do you know? We have some problem, right? So the simple solution is whenever you do context switch, probably very brutal solution is remove everything. Invalidate everything, right? Every time you do context switch, new task is running, then invalidate everything. That is too brutal, right? That is why CPU processor is providing address space ID, address space. So what does that mean? You are assigning some unique ID for each task. For example, time, right? Time, and first 1 millisecond, second 1 millisecond, task 1, task 2, 3. When task 1 is running, right? Task 1 is fully using this virtual space, and you are assigning. OS is assigning address space. That address space ID. Okay, let's say that ID is 5. Assigning unique ID. Task 2, is running. Then it's utilizing full space. Now that assign 7 to address ASID, address space. Right? And then the thing is, when you have a TLB piece, not only pitch call page number and attribute, but ASID is also loaded. ASID field, fine. So that means this translation information is for task 1. Okay. Sometimes 7, right? 7 some pitch call page number. and that entry is providing translation information. This one is translation information for task 2. So that means you don't have to invalidate TLB every time with the context switch because you have that unique ID for each task. So you have address space ID and also some register inside processor context ID. So when you run task 1, OS will program this context ID with 5 because you have to compare, right? So current address space ID, current, okay, and then stored context ID. So address space ID. That should be compared. Check. Okay, we can skip this part, I think. Okay, that is about page table and TLB. Any question? From Monday, we will talk about the last topic, trust zone, the security architecture. CPU is providing security architecture. But then it will be the last. Okay, any question? Too silent. That is not the sign. Okay, I'll see you next week. 듣는 거냐? 마스크 써갖고 표정을 못 보니까 알아듣는 거야. 못 알아듣는 거야. 알아듣는 거야. 다 포커페이스라고 했으니까 알 수가 없어 이거.
혹시 슈퍼 섹션 개념을 아직 잘 이해하지 못했는데 바로 슈퍼 섹션이 어디서 유용한 건지 알 수가 있을까요?
슈퍼 섹션을 그러니까 우리가 예를 들어서 4K 바이 섹션이라고 하면 결국은 우리가 트랜스레이션 도구가 필요한 거예요. 결국 슈퍼 어드레스를 얻고 싶은데 4K 바이 섹션에 대해서 4K 바이트와 16KB 4K 바이트와 16MB 요걸 한번 비교해 보면 굉장히 큰 사이즈니까 얘는 굉장히 큰 사이즈에 대한 변환 정보를 제공하는 거죠. 그리고 우리가 애플리케이션을 실행할 때 우리 만약에 이제 이 정보가 유용하다고 하면 언제 유용하냐면 우리 프로그램이 구현할 경우에 들어가 있습니다. 그렇지 않아? 만약에 이제 우리 프로그램이 만약에 코드 사이즈가 일단적으로 이게 16개가 있습니다. 그러면 하나의 엔트리만으로 TLB 변환 정보를 계속 제공할 수 있는 거죠. 근데 우리 프로그램이 만약에 이제 16개가 이렇게 16개가 아니라 분리가 돼 있어요. 4K 있고 브랜치를 이렇게 4K 여기 안 쓰고 하면 이제 좀 떨어져 있나? 그러면 4K로 정보가 더 이용할 수 있고
이거는 슈퍼 섹션이 이용하는
킬로바이트, 4kB 정도. 데이터의 경우가 더 오히려 설명하기 좋을 것 같아요. 만약에 우리 데이터가 뭐 영화 파일이다. 그거는 영화 파일은 그냥 차례차례 우리가 불러와서 영화를 보여주는 연속적인 공간에 연속적인 데이터가 있고 그럴 경우는 16MB 슈퍼 그거에 대해서는 연속적인 공간이 있으니까 될 수 있으니까 94kB를 쓰면 너무 많은 정보들이 내가 타이틀 하는 거 아니니까 그걸 사용하는 게 하나만 찾죠. 하나의 MP만 찾죠. 그러니까 훨씬 더 좋지. 데이터에 대한 트렌드를 경험해서 다른 PP에는 뭐 다른 트랜스레이터.
그러면 슈퍼 섹션을 사용한다 치면 이 섹션에 대해서 연속적으로 부탁이 된다는 게 보장이 된다.
그런 경우에 데이터가 아주 커갖고 영화나 파일처럼 그거에 대해 하나의 엔트리만으로 트랜스레이션이 된다라고 그럴 것 같다라고. 네. 큰 페이지를 쓰는 게 낫고 다운 페이지를 잘 돼야지 쪼개서 가까이 대해서 트랜스레이션.
어드레스 전환할 때 슈퍼 섹션이랑 섹션이랑 오버랩 4비트가 된다고. 그 의미가 사실 아까 이해했던 것 같았어.
그러니까 이제 슈퍼 섹션, 그러니까 슈퍼 섹션은 16MB 때문에
네. 옵셋이 24.
옵셋은 24야.
네.
이게 그대로 카피가 그대로 이제 붙는 거예요.
네.
피지컬 어드레스. 그리고 우리는 요 피지컬 슈퍼 섹션 번호만 이제 알아내면 되는데 그거는 페이지 테이블. 페이지 테이블이 피지컬 슈퍼 섹션 넘버를 제공하지. 요거.
그게 이제 8비트로 이제
그렇지.
8비트인데 근데 거기서 섹션이 갑자기
그러니까 에란 페이지 테이블은 섹션을 생각하고 만든 테이블이기 때문에
원래는 섹션 기준으로 나눠져 있는데 그걸 이제 찾으려면은 오버랩이 생길 수밖에 없는.
그렇지. 이게 이제 섹션 기준으로 섹션을 생각하고 만드는 테이블이잖아.
그럼 원래 1MB 단위로 다 초기화가 같아요.
1MB 단위. 그러니까 에란 테이블은 4096개의 엔트리가 있어. 요거에 상관없이. 요거에
상관없이 그냥 원래 그렇게 돼 있는데 그걸 이제 조금 더 크게 쓰고 싶어서 그냥.
그렇지. 크게 쓰고 싶을 때는 16MB에서는 16개의 엔트리가 똑같은 정보가 있다는 거죠. 그러니까 이게 암이 그렇게 아키텍처를 한 거야. 암 아키텍처를 해. 이렇게 하면 뭐 똑같은 테이블을 사용하면서 그걸 테이블 서치를 할 수 있으니까
같은 값을 넣으면 서치하려면 그래도 줄어드니까. 서치할 필요성이 줄어드니까.
아니지 똑같이 서치하는 거지.
서치는 똑같이 하는.
어드레스로 인덱싱을 해서 12비트로 인덱싱을 해서 선택을 하는 거니까. 그게 여기 암 스펙에 있는데 내가 여기 카피를 해놨거든. 여기 보면 슈퍼 섹션에 대해서 어드레스가 버추얼 어드레스가 있고 오버랩이 좀 되잖아.
네.
버추얼 어드레스가 있고 마지막 피지컬 어드레스가 나와야 되는데 그 과정을 좀
보면서 이해할 거예요.
그걸 보면 좀 확실하게 이해가 될 거예요.
과제할 때 온라인하고 숫자 눌러서 그 데이터 조절하는 거랑 링커 파일에서 방금 말씀하신 제형 주는 거랑 지금 같은 거.
그걸 내가 정확하게 얘기해 주기가 좀 어렵네. 나도 헷갈려. 이해 코드에 있는 거는 온라인 만약에 5라고 하면 2의 5승인 거라고 생각이 되고.
네, 저도 그렇게 알고 있어요.
근데 링커 스크립에 있는 거는 그냥 보지 못해. 16384 있잖아.
네.
링커 스크립. 그거하고 좀 다른 것 같아.
그러니까 과제할 때 그냥 링커 수정하는 게 뭐 정확한 거.
그렇게 하려고 했어?
네. 온라인 그쪽으로 해도
최종적으로는 그걸 확인하면 되니까 우리 엘프 파일을 확인해서 심볼 테이블을 보면 그 심볼이 어디에서 할당되는지 알게 되니까 그걸 판단할 수 있죠.